the chairman and all the members of the panel and dear participants. I'm Srinivas Golan.
Can you please share your screen?
Yes. Is my screen visible now?
Yes.
I'm Srinivas Golam. I'm presenting this on behalf of my team Nitish Verma, Aarti Nair, Butkumaruel Dharni, and Dr. Tata Sudhakar. Before I go ahead with the presentation, I would just like to show you a video of what our product does. This is on the applications of AIML in fish biomass estimation. So this is a real-time fish detection and biomass estimation system. Why we call it as intelligent is like it runs a ML algorithm which detects fishes in real time, and then the estimate of the fish length, and accordingly the biomass of it is actually calculated, and that data can be sent to in the form of an SMS to a mobile or to an FTP server. So this is the demo of that. So we can see that it detects the fishes with the, and on the top you can see the confidence level at which it considers as a fish. And now the approximate length of it and the biomass of each fish. So in this frame, this is the length of the fish and the biomass of it. This is how the validation is done in with the real fish actually. What is the length and the biomass? So now I'll go back to the presentation. By 2030, 62% of the fish food will be from aquaculture is a projection from the United Food and Agriculture Organization. Apart from that, like there's a lot of stress for the protein requirement with the growth of population. Apart from that, fisheries is a promising field for our food resources in future. So what is the problem we are solving here and what was the requirement? NIOT has a lot of open sea cages which are deployed off coast of Andaman and in Chennai. And here we rate fishes, but there are 2 to 3 things which are manually required every day, like fish feed, which a person has to go and feed. Apart from that, estimating the size of the fish, so they have to actually catch it, kill it, and then weigh it to see whether it is ready for harvesting or not. But doing this every time when in the offshore, when in the high seas where we have monsoons and all going on, it's very difficult to do it every time. And we thought of why not replace it with a IoT device which could do the fish biomass estimation. Apart from that, we can also thought of getting other parameters like water quality, for example, the pH and the dissolved oxygen, which are also required for the fish rearing and other activities. So we have come up with a system architecture where we have a module with camera and 2 laser pointers. I'll tell you what actually they do. Apart from that, there is a edge computing platform which does real-time computing, which is powered by an AIML algorithm. The other power sources and the data transmission modules which transmit the data directly to a cloud or to an FTP server, and also can be sent the data as an SMS. The output what we get is the length and the biomass and the water quality parameter, depending upon the sensors what we attach. On an overall, how we did it, like we collected the data, trained it on an RCML module, then it is ported onto a Raspberry Pi board. Then it is deployed in the water along with Coral USB Accelerator, which is our edge computing platform. How we do the length and weight estimation. This is the formula using which we do the length estimation. Like when the length is actually calculated using a mono monocular camera, and from the distance of which the object is placed. And we use two laser pointers, where the laser pointers are shown on the fish. Probably I can show you the diagram. If you see here, these two dots are nothing but the laser pointers. Using that, we calculate the relative length of the fish, and using the depth, we calculate the overall length. Once we get the length, we can calculate the weight of the fish using an allometric equation very specific to that particular species. This equation can be derived separately for each species, whatever we are farming for. So this is the overall procedure what we are performing. One is object detection. Next is calculating the length of that, and from the length we are deducing the weight. This is the overall procedure we are doing in it. The novelty of the product is like non-intrusive, so there's no need to kill a fish to get the data of how whether it is good for harvest or not. The other major important advantage what we had is the fish feed optimization, like how much of food is required to feed it based upon its growth parameters. So this is called as FCR, feed conversion ratio, which helps in general fish farming to control or optimize the fish feed, which actually reflects in the costs. Apart from that, it has an edge computing, which forms the total calculation in real time. We had some processes which are available in the other countries, which does not real time. We have to, like, this is like post processing. We have to get the videos onto the shore and perform the processing. Overall, the footprint is very small. We named it as Drishti, and it supports both off-grid and grid modes of power. It is an IP69 rated enclosure, and we can deploy it in both marine and freshwater conditions. These are overall details of our product, and we have already applied for a patent through NRDC. These are few of the initial prototypes of our device, and this is our deployment in Andaman, where we got our results, the initial results, which were very near accurate with 95% accuracy. So where we are deploying it, like SIBA, ICAR, and CMFRI. So we already have some collaborators where we started testing it according to the species what they are growing. Accuracy and valuation, we have almost like 95% accurate on an overall. We have used Google Coral Edge TPU on our machine to perform the edge computing. So the other advantage of our overall procedure is like we are also able to do the testing or recognition in turbid waters, which is difficult in the other products available in the market. So we have Aquabyte and SKB Smart, and they are very bulky. Our product is around 1.5 kg, and all the others do post-processing, where ours is real-time processing. Ours is open source. Coming to the risks, like once we deploy it in marine environment, we have the problem of biofouling, which we are taking care of. Like we need like weekly maintenance near the camera position, where we just need to clean that camera glass. Apart from that, there are not much issues or the environmental impacts noticed. The other things are like we are also trying to integrate it with automatic fish feeders based upon the output from our product, such that the total fish farming can be like an integrated automated system with less manual intervention. Pros, apart from the affordability of cost and the reduced costs for the human intervention, we have some social and psychological benefits associated with that, such that people don't need to venture into high seas whenever you have cyclones and all. Apart from that, it's like making them sustainable to increase their profits and empowering them for a better community benefit.
Excuse me, Srinivas, can you just wind it up quickly?
Yeah. So this is one of our assumption. Like the only assumption what we had is like it can detect only when the fish is sideways, and the maximum and the minimum length is around 10 to say 10 centimeters to 200 centimeters, where the average harvest length is around 55 to 70. On an overall, we are just collaborating with other ICR institutes and state governments promoting for fisheries to introduce this device. Device was also noticed by Google and was featured in the success stories by of Gold TPU. So, any questions?